talk tonight. I'll be very brief. Our speaker tonight is Giles Hammond from University of Glasgow. He's Professor of Experimental Gravitational Physics at the School of Physics and Astronomy. He did his degree and PhD at University of Birmingham. Correct me if I get any of it wrong. He's been elected a Fellow of the Royal Society of Edinburgh and a Fellow of the Institute of Physics. He's been involved in LIGO, and he is currently the chair of the Suspension and Isolation Working Group, dealing with the amazing fused silica mirror suspension system that we developed at Glasgow. I think mostly under your guidance. Most of your team that did that. And he's recently done some work on the development of MEMS gravitometers. MEMS is micro electromechanical devices, which are like silicon chips, but they're actually mechanical rather than just electronic. They combine both. These have little weights in them that move around and measure changes in gravitation down to 40 parts per billion. So that's pretty impressive. So tonight's talk is not about the work in gravitational physics, but about work he's been doing with his students, because he's also a lecturer at Glasgow University, and on the photometry of short-period asteroids, which is a student project that he's been running. So I'll hand over to Giles.
Thank you very much. Want to keep my mask on? Okay. Oh, I'm quite happy to. So. Yeah. Okay. So in terms of screen share, do I need to do anything?
Oh, make people hanging about in the dark. If I can reach. We're going to have problems with microphones, perhaps. It is screen sharing just now, so always.
Okay.
June one again. June. Screen sharing is paused. Why is screen sharing paused?
Oh, if you go to resume again, maybe at the top. There we go.
There we are.
And then I just. Right, perfect.
Right, great.
All right, well, thank you very much. Pleasure to be here. Always nice to, actually, this is the first time I've been to a society in a little bit over a year and a half, probably, and given a live talk. I've done a few over Zoom. Tonight's a hybrid meeting, but it's nice to actually kind of interact and see people again. Real pleasure. I mean, I think I was here last sort of 2013. And then I think then I was talking about some of the work on gravitational waves. But tonight I'm going to talk about something a little bit different. And that's some of the work that we've been doing for our student projects. So, of course, I teach in our 3rd and 4th year astronomy lab. And we actually sort of had to sort of really come to think about how to run these labs remotely. And that was, of course, the last couple of years we've done that. So what we essentially did was we got some time on a remote telescope, took some data, and what I'd like to talk to you about tonight is some of that data reduction. I'm going to talk specifically about short period asteroids, but in general this can be applied to many other different sort of sources that you might be wanting to look at, whether it be variable stars. Short period asteroids are quite convenient because the ones we're looking at have periods where certainly you could observe a full period in about 1 evening. Go ahead.
I think that's my most bad of being a bit.
Right, so what I'm going to talk about tonight, I'm going to start by sort of really motivating the projects. I've said a little bit about why we did it. Where's the telescope located? And how we got access to it. And then, of course, when you take images, there's a number of different things that you need to do to your images. So this is really the data reduction. So in terms of a student project, this is really good because the students get to see more data in all its sort of glory, but then they have to make the corrections to the data. So of course, we're looking here at the main corrections of bias, darks, and flat fielding. Then, quite interestingly, of course, you need to know where your telescope is pointing and you need to find your asteroid. And there's very useful bits of software out there which you may have used, and that's, of course, called plate solving. So nowadays, you don't necessarily need a finder scope. You can just point your telescope, take an image, and then you can upload that image to a plate solving service called astrometry.net. and it's got an interface with Python. So we do all of our programming in the Honours Lab in Python. And astrometry.net will essentially cross-compare, cross-correlate that image with sort of all patches of sky, and it will come back with a solution of where you're pointing. And it takes account of if your field is rotated or inverted or mirrored. So it really is quite a useful piece of software, and that allowed us, of course, to find the asteroids. Then, of course, we did some data reduction. So you can't necessarily just look at the asteroids and expect to see a nice sort of light curve, because there's a number of things going on. So first of all, the asteroid might, well, it's certainly changing its altitude during the course of the evening. So of course, because we're taking in a specific filter band, then we might get the effect of dust, so we might get some reddening in the image. So what we did for that was we looked at calibration stars and took the ratio of calibration stars to try to take out those systematic errors. And then I'll finish off just by showing you some of the light curves. So I should say that this was really kind of a bolt-on at last minute for our projects. I'd say that our astronomy program has quite a broad range of different projects, and when we run face-to-face labs, then actually we sort of split the projects into two. They're typically sort of experimental project or practical, and then there's the computational projects. And shown on the screen here are just some of the projects that we run, and we run them in semester 2, so they run through kind of start of January through to the Easter holiday. So on the practical side, we've run sort of all of these kind of activities before. So things like high resolution imaging. This is kind of like your lucky imaging, where you may take some frames with a sort of CMOS camera, so a high frame rate camera, and look at maybe double stars, and look at those with different filters. Of course, you don't get down to the diffraction limit in Scottish skies, so but it doesn't stop the students trying. You can also look, of course, at the International Space Station. So with of course these mounts nowadays, things like on our telescope, we've got a power mount. On our, we've got a 10-inch optimized Dow Kirkham, and that can actually track satellites across the sky. So we can actually do some imaging of the space station. Of course, asteroid light curves is one that we've had for a few years now. I should say actually that using the remote telescope is probably the first year we've got some really good data. Because I think when you try and do this in sort of urban skies, then you find that just the sky quality and the light pollution is really challenging. We do advanced spectroscopy, so this might be anything from daytime observing, where we might use a high resolution spectrometer to look at the spectrum of the sky. We also do a lot when Jupiter is about. Then of course we do some spectrometry put the slit across the planet, and you can use that to measure the rotation rate just by the change in the spectral lines. We've talked a little bit to some of you about solar limb darkening. So of course that's a project where we look at the optical depth as you go across the sun. I put together a project a few years ago where we were looking at the Rover delay, and that's quite a fun one. That's essentially, that was the first real sort of measurement of the speed of light, and that's by looking at the timing of the Jovian satellites. And when you see, so for example, transits or eclipses of the Jovian satellites, if you know when they're going to happen, the time that they actually happen on Earth is slightly different, because of course the light travel time across the solar system. So we can use that when Jupiter's in a good position. We have used Uranus as well, because you can actually, with Uranus, you can actually image maybe 2 or 3 of the brighter satellites, and you can actually look at sort of small pixel variations of where the satellites are compared to where they should be. And that allows you to work at the speed of light also. That's quite a fun project. And then also we make a little geomagnetic storm detection from a compass by using sort of an optical sensor to look at the compass needle. So those are our practical projects, and I'm an instrumentation person, so I usually run all these ones, but also computational. We try to get the students on one year to do a practical and the other to do a computational project. So we've got one where we've had data from the Cambridge radio telescope, where we've been looking at slowdown of the Crab pulsar. So of course the pulsar is emitting, well, it's emitting gravitational waves, but we're not quite down at the spin down limit at the moment of the crab pulsar. But most of the electromagnetic radiation is causing breaking of the pulsar, so it slows down. So it's period derivative changes as a function of time. So we can look at data, historical data from that pulsar, and actually sort of plot how the period is slowing down. And using that, you can estimate the age of the pulsar. We have solar system simulator, so that's essentially just coding in Newtonian gravity and using that to sort of estimate where the positions of the planets are. Using a set of starting conditions, so for example, given by the JPL horizon ephemeris. So that's, of course, holds the positions and velocities of planets and many minor bodies. So we can use that as starting conditions and then sort of forward propagate. And then you can do things like add in general relativistic corrections to Mercury. You can add black holes into the orbit of Jupiter, see what happens to your solar system. Nothing good happens to your solar system, it turns out, if you stick with that. So we can be lucky about that one. Of course, with our work on LIGO, we actually take the students through some, I guess, some fairly raw data from LIGO and get them to apply some of the algorithms to actually extract the binary chirp. And then we've got some data from the Dwingloo radio telescope, so looking at H1. So we're looking at galactic structure and using that to make a sort of Doppler velocity map of the rotation of the galaxy. So it's a pretty kind of packed and exciting sort of range of projects. Of course, these are only a subset of those could actually be run remotely. Of course, the data ones are not so hard. You can sort of usually kind of access those ones. The real problem was the practical ones, though. So, for example, high resolution imaging, you need lots of data storage. So we thought, well, actually, that's not really practical even to run with a remote telescope. Advanced spectroscopy, well, there wasn't really easy access to a spectrometer, so we didn't have that one running. Solar limb darkening, well, you want access to a telescope during the day, maybe possible, but wasn't sort of very forthcoming. The Roma delay turns out that certainly the last few years that's been challenging with Jupiter. It requires a lot of sort of early mornings for the students, and again, not access to telescopes because the observatory essentially are off limits for the last year and a half. And then, of course, this one, which is the geomagnetic storm detector, it really requires some practical electronics and building the magnetometer, so that wasn't possible. So actually, light curves seemed like a good way of going. So we decided, well, that's what we're going to be doing. So why asteroids? Well, of course, we could have done this for anything we want. We could have chosen some variable stars, but we decided asteroids were quite interesting objects. Because there's a lot of them out there, and there's a lot of bright ones out there, and there's also some that have relatively short periods. So some of the really sort of fast rotators are quite unstable, whereas ones that, I'd say, short period, but of the order of a few hours, they've actually got quite stable rotation periods and rates. And the idea, of course, is what you're doing is you're trying to look at sort of changes of the asteroid as a function of time, and if that is a sort of something quite stable, then you'd expect to see some kind of light curve, either because, well, maybe the albedo of the asteroid is changing, but also the shape profile, so the extent of the solid angle of reflected sunlight is changing as a function of time. So you get some kind of periodic rotation periods. And the idea, of course, is to generate a light curve. And actually, if you choose the right asteroids, then the modulation depth can be quite reasonable, actually. So we're not necessarily looking for 0.001 of a magnitude, but it can be 0.05 or so of a magnitude. So you'd like to think that that's with accurate photometry and nice linear detectors. We always think our detectors are very linear. They're never quite as linear as you want. Certainly when you start to get close to saturation, then you find that some of the little sort of niggles with CMOS and CCD detectors become a challenge. So we have to be a little bit careful with the full work capacity. So we ended up working with, actually it turned out to be quite convenient. So a couple of our demonstrators, so one was a previous undergraduate student. He'd actually gone away from the university, and he'd gone to BA flight school, so he's actually a pilot for British Airways. But he's still got a real interest in astronomy, so he still comes back when he can and helps us with the astronomy labs. So he, together with one of our PhD students who's also a demonstrator in the laboratory, they'd actually put together a remote telescope, and they were working in Almeria in Spain. And of course, there the sky quality is really very good quality, much better than Glasgow skies. Having said that, last year, of course, you might have seen in the news that at some point, Spain had snowfall, and this was just before the lab started. So we were beginning to think whether this was a really good idea, but it turned out that actually we got a lot more observing nights than we would ever have done in west of Scotland, certainly in sort of January and February. Yeah. The even better thing is that the place where they host their telescopes is it's a sort of a place where you can just rent out some dome space, and you can see this sort of whole arrangement of roll-off sheds that they've got, where each of those has a telescope. So this is a properly managed facility. So you can see that I put the web link up there. But you can essentially hire, and of course the cost depends on the amount of space you want. And there's all different packages depending on what kind of automation you want or cameras. But essentially, there is some gatekeeping, because you don't want to just open the dome and find that either it's cloudy or there's a potential for rain. So there's a lot of work's gone into building up the facility, such as it only opens the domes when there's good quality sky. There's also a site manager who's around and actually extremely helpful. So that, of course, things go wrong and things break and get unplugged and cables get damaged or whatnot. So they often go out and do some maintenance for the telescopes as well. Now, I can't remember how much the cost is. I'm sure that would be an interesting question. We sort of essentially just pay through our university budget, so we don't actually see the cost for that. I don't think it's that significant. Well, you can decide how you want to define your sky quality, but there's different sort of measures. But just to give you a sort of pictorial example, of course, so the sky is sort of on the sort of Bortle pass. It's sort of about here, around 3, whereas typically in urban Glasgow is sort of 7 or 8, which is over here. And of course, we are sort of generally in southern Spain much less prone to clouds and these sort of annoying weather fronts that come in around January and February time. Where often actually we found typically when we ran practical observing projects, could be quite demoralizing for the students, because into week 5 or 6 and they've never actually touched the telescope yet, other than during the day and the dome's closed because it's always been cloudy or raining. This meant that actually we got a lot more data early on, which I think was actually really useful for giving the students a little bit more sort of positive outlook on the project. Because of course you've got to remember as well, I think with remote teaching, it's a lot different to face-to-face teaching. So I think it is a lot harder actually. It's a lot harder for people who are teaching, but it's also a lot harder on the students as well. And the example I always like to give is it can be endlessly frustrating trying to debug a student's code remotely when you're telling them where to put the cursor, and it's like up, down, no, line above, line below. So I think you have to make it as easy as possible. So what we actually did at some point was we actually sort of worked together to make these more standardized codes that could actually run a data pipeline, and that helped a lot actually. So the telescopes that we sort of have, we actually purchased a camera for this, so a sort of large format CMOS sensor. So we sort of put together a classic combination of a nice sort of wide field refractor and a nice large format 60 megapixel CMOS camera. Of course, the file sizes are rather large, so we had to be a little bit careful with the students, because when they wanted to analyze the full frame, we had to tell them that really wasn't a good thing to do, because they sort of would grind the Python server to a halt. So we did a lot of work where we'd sort of crop the images or downsample the images. And of course, when you're doing photometry, it doesn't really matter, because you're not doing sort of you're not looking at necessarily the resolution of the image, you're actually just counting photons or counting counts from your CMOS sensor. So as long as you sort of encompass those counts, it doesn't really matter if it's over 1 pixel or 5 pixels. So actually using sort of cropped images and downsamples or binned images essentially was absolutely fine. We also have a set of Sloan photometric filters. So again, depending on the filters you want to use, whether it's Johnson filters or Sloan filters, seems like every observatory has their own type of filter. But we use the Sloan ones, and they're essentially mapped on they're what we call the Gris magnitude system. So GRIZ. G, well, it's sort of essentially a green filter. R is a red, and then I is into the infrared. We actually did most of our work for this project with the green filter, but we did actually take images in other filters as well. The plate scale, quite nice actually. I mean the full field is pretty large actually. Of course, as you get to the edge of the field, then the quality of the image isn't so good. But it means you do get a lot of sky. So actually, you can actually image a number of asteroids if you want with a single frame. So that was the system, and that worked really well. Then, of course, we had to choose, what kind of objects do we want to observe, and I think this is the really kind of, the nitty-gritty of the project where the students really start. So clearly, they don't really get to sort of define what is in the telescope system. That's kind of we have to do that prior to the project. So what they can really do is they can start to think a little bit more about what objects do they want to observe, and I think this is really good because you have limited time on the telescope, so you have to think, what are my key parameters that are going to define whether my project is going to be successful or not. So we kind of had a chat through that, and we sort of decided that there'd be a number of things that might help you decide on your asteroid. So first of all, it should be reasonably bright. And there's a lot of asteroids out there that are bright, and here we're talking about more than 12 magnitude, and you can easily get that in 300-second exposure with this telescope, probably even less. We wanted a rotation period of probably less than 8 hours, mainly because at the time that was sort of the length of time you get in the night. So if you want to actually just observe a full rotation period, if you have like 24 hours, then clearly you're not going to see it. What you can, of course, do is you can take multiple nights of data and essentially stitch them together. So, of course, if the period is not a multiple of 24 hours, then you get a phase lag across the images. We want it to be visible throughout the night. So it doesn't necessarily have to be circumpolar, but you want it to be not sort of setting after half the period. And another one, reasonable magnitude variation. So delta M should be more than 1,000th of a magnitude, because I think then you're struggling, or 100th even, I think you're struggling. So that, of course, gave the students a little bit of framework to start going away and thinking about asteroids. And it's not so easy even then to say, well, which asteroids do I choose? Because if you look at your stellarium or whatever, it won't necessarily tell you all that information. Of course, it will tell you sort of the information about the brightness. It will tell you about when it's rising and setting for the location. But it won't necessarily tell you about the rotation period or the magnitude of the modulation. So what you need to do is a little bit of a hybrid approach, where you choose and you sort of down select a bunch of asteroids, and then you have to do a little bit of citation searching, because the Minor Planets database, of course, there are light curves that have been imaged of different asteroids. There are papers written on these asteroids, so it gets the students into the whole kind of searching for information in published resources. So no Wikipedia resources. We don't allow those. Well, you get marked down if you use Wikipedia. It's a great source for starting off looking for stuff, but of course it's not. It's generally not peer reviewed, so we can't use that as a. Well, I have to say the only caveat to that is some of the statistical stuff on Wikipedia is really good. But you've got to be a little bit careful about some of the other bits and pieces. So we usually use it as a sort of launch pad to go and find the real sort of cited work. So they did a little bit of searching, and they came up with some different objects, and there was a couple of asteroids that we decided to go for. So one was Philomela, magnitude 11, and the other was Amphitrite, magnitude 10.1. So those seem like good objects to go for, and we did take data on all of them and over several nights. Actually, I think tonight I only showed data for one of the asteroids. I just haven't got around to running the code for the other ones. But I think come next year we'll choose a different set of asteroids, I think. But again, you can see that these are sort of nice and bright, easy to capture, lots of good signal to noise. So then you go to your favorite sort of program and start to decide where are your objects. So it's a bit hard to see on the resolution, but well, here's Philomela, and it was so it's sitting down here, and here's Gemini, and there's Amphitrite sitting up there, just south of Leo. Of course, this is an interesting area, but you know, there's lots of asteroids here. So each of these little yellow dots. So if you're using Cartan CL, so it's a nice kind of, I think it's quite good actually. Cartan CL, it's a sort of freeware planetarium software. You can download the Minor Planets database. You can upload the orbital ephemeroids of the asteroids. So that's the other thing to tell the students, that they're asteroids. So you have to upload the orbital elements, because if you don't do that and you look at them and they're out of date, your asteroid's not going to be where you expect it to be. So all these useful things is always good for, you know, every day is a school day, I think, and we all learn these things when we do them. But there's a lot of asteroids around here, so they were sort of going around and choosing different objects and doing a little bit of citation searches. So I think actually in terms of the ethos of, you know, learning and taking kind of ownership of your projects, it's a nice one actually, because you know, it's just like you would do with any observing project. You've got to have a plan. You've got to know what you're looking for. You know, how many dark frames you're going to take, how many flat fields you're going to take, how many bias frames you're going to take. You're going to take the dark frames at the start of the night, at the end of the night, in between. You know, they get to think about all of that, and of course they do it a few times, and there's a few mistakes occasionally. But it is a learning process. So. And I think given that we have, you know, more clear telescope time than we needed, then we could actually allow for those variations. I think, to be honest, when you're in Glasgow doing it, it's much harder actually, because there's so few clear nights, you actually have to really get it right actually. So typically you have to sort of watch them a lot more carefully, the students. So. But some of them haven't necessarily looked at a telescope or sort of used a telescope. So although they're doing an astronomy degree, they might, you know, they may not be sort of, you know, really up to speed with it. So it's quite a big learning curve for them. Essentially, what we did was we took lots of data. So yeah, the full frame is 466 megabytes. Of course, we did crop images and we did do some downsampling of images. We took bias frames. We took a whole bunch of different dark frames. I think our image frames were mainly 300 seconds, but and of course, so essentially your bias frames are essentially as short exposure as you can take. So you just get the readout noise of the sensor. Your dark frames, you're looking essentially at thermal noise, because you can't tell the difference between an electron in your silicon that's been generated from a thermal agitation versus one that's been generated from a photon. They're just electrons in the end, and you count them. But you can actually look at sort of hot pixels, so you can look at the statistical variations and extract those. Of course, you can usually see what a hot pixel looks like compared to an object, because certainly in this telescope where you've got seeing of, I mean, the seeing's not, I mean, it's okay, it's not great, it's a bit better than Glasgow, but it's still 1.5 arc seconds probably. So of course, you know, a star sits over a few pixels, if it's 0.7 arc seconds per pixel, so it's maybe 3 or 4 pixels just sitting over. Clearly, a hot pixel is a single object. So actually, we did a few. Of course, you can do a lot of sort of reducing the dark noise by subtracting the dark frame. But you can also go in there afterwards and start looking at the images and looking for just sort of single pixels that look statistically high. And then what we do is we sort of go in and then sort of do nearest neighbor reduction, and that's what, you know, all these programs like PixInsight, you can have different sort of filters to take out these hot pixels. So even if you don't have a dark frame, you can still do a lot with it. And then of course we took flat frames, so that was just actually the inside of the dome, and that's of course to look at sort of non-uniform illumination. So you might have vignetting, and we have lots of vignetting in our system because of the large field of view. It might be dust, so of course sensors get dust on them, dust donuts, so we can take that off. And then also your CCD might have fixed pattern noise, or they will do, or your CMOS sensor might have some fixed pattern noise. So there might be sort of variations across the sensor itself. So we took all those frames and then we had them all in our directories, all nicely labeled. So these are the ones you really shouldn't use, because if you're trying to kind of operate on these large files frames and you've got 100 of them to go through, that's not really conducive for the server. So we often worked with smaller frames, crop frames. So we sort of work out where the asteroid was and then go and crop the frame at the appropriate place. So in terms of the software analysis, so we don't give the students an easy ride. So you can do all of this in sort of Astro Image J, and it works really well. But we actually, from year 1 to year 4 or 5, which is when the students graduate, we have sort of what we call vertical integration. So we require the students to use the programming language that they learned from their first year. And in this case, we recently switched, well, 2 or 3 years ago, we switched over to Python. So we used to use MATLAB, and of course that was challenging because with MATLAB you need a license. So it was not easy for students to get access, but of course Python is just, you download it and it's extremely powerful. So you can do a lot of analysis. And also we have something called Jupyter Hub, which is essentially, it's an online server that you can actually do your coding, so that you don't actually need the Python on your own machine, but you can actually use it on our server. So what we did, of course, was sort of think about the data pipeline and how you want to analyze your images. And everyone who does astrophotography, everybody had their own kind of way of kind of running through images. So not saying this is the right way to do it, but everybody's got their own way of doing it. But we'd read in the image files, we'd do some calibration files. So when we're doing the calibration files, we'll typically sort of sum together 10 to 20 bias, flat field, dark frames. And what you're doing there is you're generating your master frames, your master dark, your master flat, your master bias. And those are the ones that we work on, because essentially what you want to do is you want to sum up the dark, flat and bias frames, because you don't want to be adding excess noise into your images. So by summing them up, you can reduce the noise, keep the signal, of course. Then we do the plate solving, and that's really to work out the white ascension declination. And I don't know if you haven't used plate solving before, I think it's fantastic. I'm a convert. The fact that you can take an image and just upload it and it tells you where you're pointing, it really is quite a neat thing. Once you've got your white ascension declination, you can work out where your asteroid is. And then, of course, when you've got your asteroid, you can then start to say, well, I'm going to choose some calibration stars nearby. And of course, your calibration stars should not be variable stars. That's sometimes easier than, you don't always know. It's quite hard to find the source of some of the calibration stars to make sure they're not varying. But I think we found sort of, we had typically about 13 in our field of view, of which, well, I'll tell the story later. It turned out using all 13 wasn't the best thing to do. Using 1 or 2 was much better. But then we'd use those calibration stars essentially to work out the magnitude of the asteroid. Because essentially what you're doing is you've got counts coming out of your CMOS sensor. So you don't know whether it's 10.1 magnitude, all you know is it's 25,000 counts in the analog to digital converter. So somehow you've got to turn that back into a magnitude. And the way we do that is with something called Aperture Photometry. So we'll go through that a little bit later as well. In terms of the corrections, so we typically take the sort of raw source image, we subtract the dark, and of course that takes account already of our bias because we've got the bias in both of those. Then we'll take the flat fields and we divide them by each other, and then we multiply by the mean of this on the bottom. And that's just to properly scale. So it's quite interesting, of course, when so often some of these programs, things like PixInsight, they'll do it for you. But when you actually do the coding yourself, I'll give you an example. I think I've got an example here. So imagine we've got sort of some image parameters. So let's say we've got a 16-bit image. So a 16-bit image means we've got 2 to the 16 sort of essentially levels from black to white or white to black. So let's say 0 is no light, so it's black, and 2 to the 16, which is 65,536, is white, or because you got 0, it'll be 65,535. And then anywhere in between will be grey. So of course that's why 16-bit cameras work well, because they've got a lot of dynamic range, much better than an 8-bit webcam, which has 256 levels. So let's say the flat field is sort of, just a little bit less than half full on capacity, so 23,000 counts. Your burst frame is quite low because it's the readout noise. Maybe the dark frame is 500, but your signal frame is 5,000. And then you say, okay, well, now I'm going to do the correction. And if you do the correction there, and you say, okay, I'll take my signal frame 5,000 minus my dark, which is 500, so that's 4,500. And I'm going to divide it by my flat minus my bias. And of course, if you do that, you get 0.196. And if you plot that, everything will be black. Because the way that Python or MATLAB or whatever program you're using will kind of interpret this is it will interpret as a 16-bit number. So 0 is black. It doesn't matter that you've got quite a lot of signal here. You just kind of divide it by a big number. So that's why you have to then renormalize it by the mean, and that's what PixInsight will do. But it will do it sort of in a way that you might not always see it. So of course, when we do the sort of corrected version, we do this, and then we multiply by the sort of mean. I call it the mean because when you've got a full image of 4,000 by 4,000 pixels, then what you do is you sum up all of the pixels and work out the mean of the image. And that ensures that your flat field essentially is normalized between, it's got a mean of unity. So when you do that again, you end up with 4,500, which is kind of what you expect. It's your signal minus your dark frame. So that's an important step. So again, it's a useful learning process for the students, because when they plot it to start with and they find everything's black and they think, oh, what's happened here? And then you can actually start to talk to them about, how numbers are essentially stored in your code and your computer and how it interprets, because all it's doing is interpreting a number between 0 and 65,536. Then, of course, you can sort of look at sort of stretching, and everyone who does astrophotography, you'll all love stretching of images. So here we limited ourselves just purely to linear stretching because we were interested in doing photometry. Of course, if you're doing sort of maybe some deep sky astrophotography, you'll do a non-linear stretch probably. So what we do essentially is, okay, here again this is black at 0 and white sitting up at 65,535, which should really be. But actually, most of your images might be sitting here. And what stretching does, of course, is it sort of rescales the dynamic range, because if you've got no data here, well, you can just rescale this black region up to here. So this is the new black, and then the white region, you scale it down to here. This is the new white. So now your dynamic range, this is black, this is white. So you essentially stretch the image, and that means that if you just plot this normally, you get some fuzzy blob in the middle of your screen. But then when you rescale to the yellow, then you get a brighter image. And of course, monitors are really not very good at displaying kind of high dynamic range imaging. So what you then do with the stretching is we then get this sort of spread from black now, the new black and the new white. And there's your image here. So you're using up optimally the dynamic range of your monitor. But then you can talk about linear stretching. So of course, linear stretching is a linear line that runs between the sort of cutoff that you're interested in versus your black and your white that you're going to plot. So it's just a linear line. A non-linear stretch would be that you've got some kind of polynomial. It might be a white and a half, or it might be a logarithmic. And of course, if you want to kind of pull out, if you've got lots of data at really low frequencies, then you might stretch it in a certain way to pull the faint objects out. But of course, the price you pay, you never get anything for free. Stretching always brings about noise and artifacts, because they're always there. You just don't see them when you're looking at your sort of 8-bit monitor. But when you really start to stretch quite aggressively, then those things come about and you start to see them. So that's really quite useful, and we can do we do a little bit of stretching in Python. That's quite fun to do. You have to get your head around sort of polynomial fitting, but it's always good for them to do. But then, of course, here we go. These are different sort of frames. So this is our bias frame. So yeah, it's fairly kind of in stretch, it's sort of very, very low count, around a few hundred. This is the dark frame. Of course, you don't see anything, but there are all the hot pixels there when you zoom in, just not the resolution of that sort of full frame image. So these are 300-second dark frames. And then we've got probably the flat field next, I guess. So there's our flat fields. And you can see there we've got lots of vignetting. It looks worse than it is because we're stretching the image, but you can generally see that it's bright here and it falls off towards the edge. So we've got some effects of the large frame format of our CCD. So we can take account of that to some extent by doing the correction. And then we have to find the asteroids. So then we do the plate solving. So we've now got our image, we've summed up our bias, our darks, our flats. We've done the correction according to that equation. And that's a sort of pixel by pixel correction. And now we've got a corrected frame. And that corrected frame has some stars in it. And we've got to sort of assign those stars. And we've got to work out where on earth on the sky we're pointing. Well, of course, we know roughly where we're pointing because it's a go-to mount. But it's important to actually do the correct plate solving. Actually find the asteroids. It's not easy to find where the asteroid is because it moves. So each night it's in a slightly different part of the sky, of course. So, of course, knowing where you are is useful for finding your calibration stars also. It's useful for finding your asteroids. So we use this thing, it's got a Python interface, but you can just upload your images to it. It's called astrometry.net. I don't know if anybody's used it, but it really is quite good. So you take your FITS file, you upload it, and it churns away for a short time, and then it comes back with a solution. It says, this is where you're pointing. It tells you things like this is your plate scale. So it's a nice sort of check of your data. And it takes account of things like, as I say, rotation, flipping, even a little bit of skewing of the field, so it does affine transformations for you. So then when you've done the plate solving, on Python you can actually then start to plot grids of right ascension and declination. And sorry, these are really small, but these are just the lines of, I forget exactly, but it's every sort of 5 seconds, I think, on there. And then we sort of label kind of other objects. So in order to do the plate solving, you have to give it some stars. So there's two ways you can do the plate solving. So one, maybe I've got a bigger image in the next slide. I'll show you that. So there's two ways you can do the plate solving. So you can upload the full image, the FITS file, and while that's fine, it's actually not a very efficient way to do it because the FITS file might be 60 megabytes. So what we actually do with Python is we actually use an algorithm within Python, and it actually identifies stars in the image. So, of course, these are stars. They're only I mean, you can see that almost a pixel, so only about four pixels. But there's a sort of, a star has a sort of Gaussian kind of envelope on the CMOS detector. A hot pixel, of course, would be a single pixel. So depending on you can sort of set the star finding algorithm to kind of lock into different things. So look at, for example, how bright is the object compared to the background. So the background's grey and the stars here, it's just an inverted image, a sort of blackiness. So you can set a threshold, so you look for the really bright objects, and you can also decide to look for things with a certain width. And then you kind of tune those parameters until you get enough stars in the image. And you can see here there's 110, so I suspect we're looking for about 400 stars in the image. And the nice thing about this is that what astrometry.net and the Python interface do is that the star finder just finds these objects and just uploads the 2 coordinates of the objects in pixel values. So it only uploads a set of 400 data lines, which is much smaller than the actual sort of full FITS file. And it still does the solution absolutely fine, and it returns the center pixel and the plate scale, and then you can sort of calibrate your image. So we did that. We found a number of stars. These are not ones that we actually use, other than we want to use them as plate solving objects. And then there's a few that are highlighted in blue and red. So these are ones that we decided to use as calibration stars. So the yellow circles are just stellar objects that have been identified. Could be the asteroid as well, so there is a little bit of error sometimes. And then the blue circles are our calibration stars. You can see that they're numbered as well, 1 and 2 there. And then I'll show you that later, but the red circles are what we use for aperture photometry. So then we decided, well, okay, we know where we're looking. It's quite a useful exercise that the students can actually sort of predict where the asteroid should be. So actually, again, this is quite a nice site if you want to go look at it. It's called JPL Horizons, so Jet Propulsion Laboratory. So they hold essentially a data archive of the solar system. So you can actually search for lots of different bodies there. So for example, here we're looking, so on Earth, we're looking for amphitrites. So you can put the number in, or you can put the name in. You can put the latitude and longitude of the observatory in Spain. You can ask it when to search for. So this was sort of March last year, the 10th to the 11th of March, in steps of 1 hour. And then you can output the right ascension declination. So as a function of date and time, this will tell you where amphitrite is on the sky. And then the students can kind of code that and work out. They can use it in their Python code, and they can actually track the asteroid across the sky, because you know every time you take an image, you know when it's been taken in terms of time. So you've got a sort of fit essentially of time versus position, and they can actually put a circle around the asteroid and predict where it is and do aperture photometry on the asteroids. So that's quite a nice thing to do. So this is a really useful database. So now we're looking at a bit, and now the purple. This is where the asteroid is. So this is amphitrite, and of course it thinks the plate solver thinks it's a star, but it's not a star. It's the asteroid. It's a little bit off because our resolution is every hour, so the asteroid is moving away from the box, of course. So it sort of gradually tracks across the sky. So if you take it, of course, from the start to the end of the night, and I'll show you an image in a minute, you can do blink analysis and work out where it is. These are all the calibration stars that we found. And because we've got such a large field of view, we had probably about 15 or so in some of the images. As I said, we only used probably about 2 or 3 calibration stars in the end. But that's the right ascension declination of the object, amphitrite. And then, of course, what we did then was I used PixInsight just to show the students. I cheated a little bit, but you can do this with Python as well. And they're centered on the asteroid, and they're centered on the asteroid. And you can see here that, okay, this star here has moved a little bit. So this is 2 objects about 8 hours apart over the course of the night. And then, of course, we can do more than that. We can just do it out of the way. So there you go, there's the blink analysis. So that's sort of essentially plate stacking. So you've actually stacked up all the images. Well, the 2 images at the start of the night and the end of the night. You register them together with the stars, and then you can just take the difference. And of course, PixInsight has this nice ability to do blinking analysis, and there you can see the asteroid moving. So then the students can then sort of check that really they're seeing the asteroid as they expect. So now we've properly calibrated, we know where the object is. We can actually now use our Python code to do the photometry. So we say, well, find the object that's closest to that purple circle, and then determine how many counts there are sitting in that asteroid. And then we can compare that to our calibration stars, and then we can work out the magnitude of the asteroids. So yeah, we don't know that yet. All we do is we can count the number of counts in those little circles, and it will tell us so many sort of analog to digital units. So then we need calibration stars to turn that into a magnitude. So again, there's a number of resources out there. So we're using, this is another really useful website called Vizier. And you can actually search for there's a whole variety of catalogs in there. So for example, there's the Gaia catalog, if you want to search for that. But we were essentially using the GRI filters, or the GRIS magnitude system. So what we had was we were able to find for a specific location. So of course we know the center RA and declination of our asteroid. So you can then stick that in it's 120 degrees, 22.9 in declination. You can search, this is 30 arc minutes. So it's about half a degree we're searching. So that's roughly, it's about 1 degree out field of view. And what you can do is you can then search for essentially the different magnitudes of the object. So there's the B magnitude, the V magnitude, so these are the Johnson filters. But then these are being converted into, it's hard to see here, but the GRIZ system. So we've got actually calibrated G magnitude, R magnitude, I magnitude for different stars in that field of view that we choose. So we use the right ascension, 10 degrees, 11 minutes, we use the declination, and we did a search, and then that came up with a list of calibration stars, which are these ones here. So we started off, we've got about 22 stars there. So we've got the B magnitude, the V magnitude, the J magnitude, the H and the K. So these are all Johnson filter bands. So that's a specific calibration system. And actually that's where that's the native system of where those images were taken. And then what this paper has done, which is kind of doing the calibration, is it's converting those into the new filter band system, which is the GRIZ system. So of course what you need to know there is the width of the B and the V and the J and the H and the K bands, and the width of the GRIZ bands, and you can sort of map the flux across. It doesn't map always very well, so some of the ones in red are not very accurate, but here not very accurate means probably better than sort of 0.01, 0.02 of a magnitude. So the sort of final decimal place. But we're using the G band, so these are our stars. And you can see actually the calibration stars conveniently are all based on the magnitude of the asteroids, which is of course another sort of useful thing. If your calibration stars were 18th magnitude, then you'd be struggling because you wouldn't see them in the field of view. Or you need a much longer exposure, and then you, of course you saturate your asteroids. So this was actually quite nice. So we started off looking at all of the stars, and it turns out that because all of these stars have different spectral classes, they're not all like the sun. So that turned out to add some statistical error into our data. So we ended up just choosing 2 or 3 stars which were sort of very similar spectral type to the sun. So we were choosing sort of like G0 type stars or similar to that. So I think I'd probably say which ones we were using. So there's one G0V. So the sun's like a G2V. So there's no sort of G2V there, but there's a G0V, there's a G2IV, G24, and a G05. So those are kind of spectrally close enough. So we actually just use these 3 calibration stars. So why do we have 3? Well, we use one to calibrate the asteroid, and then we used the other to kind of self-calibrate the image. So what we did was we used, let's say, I forget which one it was, but let's say we used the middle one to just calibrate the asteroid, and then we used that star to calibrate these 2 magnitudes, and then we took the division of these 2. And we'd expect, because those are standard calibration stars, they should be flat. And the asteroid then hopefully is showing some statistical variation in its light curve. And of course, if you're seeing just as much variation in your calibration stars as you are in your asteroid, then there's really no statistically significant measurement that's being performed. So we use that as a way to try to test whether we're actually seeing something in the data. Now, before we can do that, of course, we need to do aperture photometry. And again, this is a nice tool that, again, PixInsight will do this, AstroImage will do this. But it's kind of nice to see where it comes from. Aperture photometry, what it does is it takes an object here and it draws 2 circles, and you have the choice and you can decide what's the radii of the circles. But here we've got R1 and R2. So then what it does essentially is it works out, or it estimates the background and it estimates the object brightness. And of course the problem here is that when you take this circle, when you just count the number of photons in this inner circle, you've got the source here, but you've got the background. And you don't want the background, so you have to take the background out. So the way we take the background out is we do this aperture. And then some also do a 3rd aperture as well, but here we just did 1 aperture. So essentially our background, what we do is we count the number of ABC counts in that annulus. And then what we do is we work out the number of counts in that sort of R1 and R2 and divide by the area of that annulus. So it's pi r2 squared minus pi r1 squared. So pi r squared is of course the area of the circle. And what you do is you take that circle area minus that circle, and that just leaves the outside bit. We count up the number of counts in there, and that's our estimate for background. And then what we do is we do the same, the object counts, and then going to be the counts in that inner circle minus the background you just worked out from the annulus times pi r1 squared. So you extract all of these sort of background counts, and then you're just left with the source. And that's the idea of aperture photometry. So it's the idea of trying to make an estimate of your background and then using that to subtract from the image frame, which is polluted by the background. And that works really well. Of course, you have to be a little bit careful. So we had another group working on a cluster, doing some cluster photometry, and they had an endless problem because when you have quite a crowded field, not like this image, then if you've got another object sitting in that annulus, you have to be really careful. So it turns out that what you can do with aperture photometry is you can actually mask different regions. So if you've got an object that's sitting in there, you can actually mask out bits of the circle and it'll actually take account of that. But the kind of basic premise is that you image something, you put some circles, and of course you can play around with different sort of choices of circle, because if the inner circle is too tight, you start to clip your star. And if it's too broad, then you pick up other stars. So again, the students have the opportunity. I think it's important to experiment, because what they can do is they can do some sort of different kind of estimates where they can change the area of the circle, starting from too small to too large. But what, of course, you see is that the curve rises and then it sort of flattens off. The point that you get to flattening, that's where you want to pick your sort of inner radii. And then, of course, you can have a play around with the outer radii, and if you make it too big, then you start to get other sources in there. But it worked quite well for us, aperture photometry. So then we had to kind of convert that back into magnitudes, and we used, so essentially what you've got is you've got the asteroid counts, or the object counts from the asteroid, and the object counts from your calibration star. You know the magnitude of the calibration star in the G band. So what you then do is you say, well, okay, the asteroid magnitude is the magnitude of the star, and of course the magnitude scale is logarithmic. So in order to work out the magnitude, of course, if these are equal, then that's unity, and the log of unity is 0. So then that, by definition, the asteroid is the same brightness as your star. If this is a factor of 10, if the star is a factor of 10 brighter, then that's a log base 10 of 10. So you get 1 times 2.5. So that's you get sort of 2.5 added onto your magnitude. And if it's dimmer and it's 10 to minus 1, then you get minus 2.5. So this is a way that you can take your calibration star, because you know that, and you now know those two things from aperture photometry. So now you can estimate your asteroid magnitude. And that's what we did. And we did that for the asteroids. And we also did it for, as I said, another 2 calibration stars. So I think that's what we did in the end. So we took the asteroid, which is this one here. We took, remember there were 3 stars that were sort of highlighted in that table, and I don't recall which one was which, but we took one of them to be a calibration star, and we said, okay, that's the one we're going to use to estimate the asteroid magnitude, but we're also going to use that to estimate the brightness of those 2 stars, reference star 1 and reference star 2. And then what we did was we actually divided reference star 1 by, we looked at the ratio of brightness. Or we looked, are they varying as a function of time? And that's a way of trying to estimate, if everything's varying, then there's no sort of, as I say, statistical significance to the observation. And there's nothing wrong with that. I mean, this is not that, labs are not that we have to get, the result that we expect. Often you don't get the result you expect. And then the interesting thing is, why did it give the result we expect? Is there sort of excess noise in the system? Is it the sky quality is not good enough? Is it the camera problem? Is it a problem with our biased dark frames? Whatever it could be. So it's not a problem if we don't get the expected result, but actually having some understanding of where the problems are, what would you do to fix it next time is the important thing. So that's what we did. We took the 2 reference stars, we took the asteroid magnitude, and this is maybe one of the last slides, but we then sort of plotted them against each other as a function of time. So we took 2 nights of data, and I think I'm only plotting one of the reference stars here, but you can see here, so this is now in magnitudes. So the magnitudes are close to 10, so that's good, because we expected amphitrite was going to be around 10.1, I suspect, depending on, of course, the time where it is in its orbit, it changes its brightness a little bit. So it's around a 10th magnitude we're expecting. And we're expecting about a 0.1 magnitude variation. So it's quite a big dip. So you can see here that actually, you know, okay, you might think, well, there is some kind of periodicity in there. And interestingly, we took 2 nights of data and we could see the same sort of thing happening with the asteroid. Whereas when we looked at the standard reference star, this was actually much tighter. So our reference star is actually plotted on here, so it's a little bit dimmer, it's 11th magnitude. You can see the reference star is not really moving by more than maybe 0.02 of a magnitude, whereas our asteroid is varying by almost 1 of a magnitude, and that's kind of the sort of delta M that we'd expect in this object. So, you know, statistically, well, I would say you don't have enough data there, really. It would have been nice to take even more data. And so we do have more data, just haven't analysed it. Because if you can take multiple nights, and you can say, well, actually, you know, that's stitched together with the end here, and that is really a sort of 6-7 hour period, which is what we expect. Then if you take it on a subsequent night, then you can start to put these curves together, and if you're always seeing the same and you expect it to be a standard rotator, then this gives more emphasis to your hypothesis that you've really seen something. But actually, if you did a chi-squared test on that, and there you'd say, well, okay, you know, is this something statistically significant in that? Then I'd say, because you don't see anything in the reference star, and you do actually see structure in the asteroid, then probably there is some statistically significant signal. So yeah, I think the bottom line was, you know, reference stars were not changing significantly, but the asteroid was showing a variation that's consistent with the magnitude variation, really consistent with the light curve period that we're expecting. So we should go back next year and observe it again and do some more observations. I think that's about it for the talk. I'm very happy to answer any questions, but I think the main takeaway from this was, you know, this kind of started as a fun sort of project, but I think, you know, it taught the students a lot of the good sort of housekeeping of what to do with the data, how to search for objects, how to sort of, you know, prioritize what you're going to look at in a night, how to do good data reduction, and how to look a little bit about your plate solving, how to do photometry, and how to sort of really assess whether you've seen some kind of signal in your data. So I think it worked really well, and we'll certainly be running it next semester in 2022, and we may choose the same asteroids again, but we might also choose some other ones. So thank you, Clive.
Did you only get data over 2 nights?
No, we did get actually more data. So we probably took in the end probably about 8 or 9 nights of data. We just haven't. I haven't analysed any more of that data. I think probably the students did. Yeah, we do have more data. And again, you know, I would say that, you know, this is just sort of available data. So if anybody would be interested in it, I'm sure we could put it on a server where you get access to it, because it's kind of fun to play around with on all those wet nights when you can't do any observing.
Another thing I was interested in was the bias curve, and I think you said the bias curve is included in the dark curve. Because I mean,
because it's a sort of exposure. It's a readout noise.
Yeah. So if you're taking a dark frame, then when you read out the dark frame, the bias frame must be within that. Yeah, that's what I'm saying. Yeah. So the equation actually has a subtraction of the dark frame on the top. But on the bottom, you're subtracting the bias frame from something else. So,
it's a flat.
So you're subtracting the bias from the flat.
Yeah. I mean, there's a bit of an assumption there that, I mean, what we're really saying is that the flat has a very small contribution due to the bias, because it's typically about 60% full wall capacity. So I think formally we should probably do we should actually probably do the same. I mean, if it's a flat minus a dark, then they've both got bias in them as well, actually. Yeah. So as soon as you're taking two, I mean, on the numerator we've got image frame minus dark, so that takes account of the bias. On the bottom it was flat minus dark.
Flat minus bias.
Flat minus bias, yeah. So because you've only got one frame of the flat, that's why we subtracted the bias from the denominator.
Right, yeah, I'm just interested because that's a sort of a debate and.
Yeah, absolutely.
Whether you actually need bias frames at all.
Yeah.
But you seem to think it's necessary.
Well, I mean, we've not really, I mean, that'll be another interesting project on its own, actually. To you know, if you were doing the photometry, it'd be interesting to say, you know, if you do, you know, if you don't include the bias frames, how much does that skew your data? It doesn't skew it at all, actually. And it may not be. I mean, I've seen people as well that they don't use a division. They do a sort of full subtraction of the flats. So yeah, I don't know. I think there's a lot of different formulas out there that are doing correction.
Yeah, it's interesting.
So what do you do?
Yeah, well, the software I use, you have the opportunity to use bias frames,
Yeah.
and having done it with and without bias frames, I don't see much difference.
No.
But then this is actual photography; it's not photometry.
Yeah.
So that's different anyway. So.
Yeah, I mean, I think actually certainly for the bias, I mean, the bias noise of these cameras is actually so low. I suspect that's why you don't really see much of a difference. I think. Yeah.
There's a question from one of our viewers on YouTube asking the histogram, black and white graph showing the histogram of the images captured, or did it show the changes in light levels over time?
Oh yeah. Oh, I think about. Oh well.
Right, back on.
That's all. Oh, no, I can't move my mouse. We shall answer your question in the try to answer your question. I am. Right, that one there. So this is really, this is assuming you take an image. So your image is going to be between black and white. And all this is saying, so this is just one 300-second frame. So this is an image frame taken at a certain time, and it's got a duration of 300 seconds. And what we're saying is that this is a histogram plot now. So really the histogram is telling you how many pixels are black, how many pixels are white. And what you can see here, if I get my head out of the way, well, if I get the right. It's probably hard to do this backwards, isn't it?
There we go.
You'd have thought I'd know by now, actually, wouldn't you, about how to drive a PowerPoint presentation. So this is a histogram, so it's telling you how many, essentially, how many pixels you have of a certain color. So it's telling you that most of the image here is sort of kind of mid-range, so it's 13,000 to 26,000 pixels. So it is a single image. And what we're doing now is we're saying, well, actually, there's not much data in the lower half, and there's not much data in the higher half. There is data there, but there's just not much of it. If you plotted that on a log scale, you probably would see some data. So what we're just saying is we redefine where black and white is, and redefining the black and the white just means that we can actually use more efficiently. You know, the projector screen here might just be 8 bits of green, red, and blue. So we've only got 256 levels of color. So it means we don't have the dynamic range to show this sort of very detailed image. So if we can redefine that, we can actually show it much more clearly on a screen. So this is what we call stretching, or in this case, linear stretching. But you will have some pixels will be saturated, so they will be purely white, and some will be undersaturated.
Yeah, this makes sense. Yeah.
Oh, I like it.
Yeah, that's it. Cool. If there's any questions on the Zoom side of things, there's nothing come up in the chat.
No.
So Phil again.
Yeah, I was wondering why you went from Johnson to Sloan filters. Is that just because Sloan is the new standard?
Yeah, I mean, really, it's just the ones we had on the telescope.
Yeah, that's the other thing.
Yeah.
Yeah, I take it the hosting site provides the telescope and cameras and filters for you. You buy them or you rent them. We bought that stuff actually. So that essentially we already had some filters available to us. So because these are rather large format cameras, the filters aren't cheap. So we just decided to use the Gris filters that we already had actually. Yeah, I think that's right. But as you say, everybody's got their own filters as well. I mean, I think GRIZ are becoming fairly mainstream standard now actually. So a lot of the Gaia work is sort of, or GDAS filters, they're very similar to the Gris system. So yeah, it was available technology. But you know, for example, we bought the camera and we installed it on the telescope. So all of the hardware is purchased. We really just rent the
the space and the dome all the enough sheds.
Get the chat window up on Zoom.
Yeah, I don't see anything on the chats.
You usually have a number there if it's got.
Yeah, a little red number or something.
Nothing.
No.
No chat.
Go on, type a message in Zoom chat if you want, but yes, we'll take a lot.
I'm very interested in the aperture
Yeah, photometry.
photometry. Back in the 60s, I was using a sort of electromechanical machine called a Becker iris photometer for reducing photographic plates of star clusters. And on a big ground glass screen, we centered up the star inside this iris and then contracted the iris down until a fixed amount of light was getting through.
Right.
You recorded the size of the
Oh, fantastic! That's great.
and then calibrated
That's
the
great,
stars.
isn't it?
So,
Yeah.
it's-
Haven't things changed? I remember when I did my undergraduate degree actually, and at that time it was everything was sort of Palomar sky plates. And we had like these big sort of photographic plates. And it was like, the globular cluster. And students were like sort of taking a little eyeglass and sort of putting grid paper down and sort of looking through an eyeglass and counting stars. And you think nowadays, how things have changed, and it is interesting. But it's interesting, it's the same kind of concepts of, you're stepping down the iris, and presumably you could do that, and you could have made amendments if you wanted and made an estimate of the background as well, doing that.
Never thought of that.
Yeah, that's interesting, isn't it? But things like blink analysis as well, for searching for supernovae.
The microscope.
Yeah, I mean, that's been around forever, and it's great to see that it's now in a sort of more electronic form that you can just sort of cross compare two images really quickly. And it is so powerful, actually. You forget these things, I mean, in terms of just plotting the two images with registered stars, the asteroid just pops out.
Yeah.
Whereas if you're sort of digging through the right ascension declination, it's really quite hard sometimes to,
Right, I think we've got no more questions. Nothing
Okay.
in the chat, nothing on Zoom, nothing on
Alright.
YouTube. So
reading that to myself. So.
thank you again. Those on Zoom as well. So I think that kind of wraps things up for now. Unfortunately, due to COVID restrictions, there's no tea break, so I can't offer you a refreshment.
No worries.
But thank you very much.
Pleasure.
Giles. And,
Well, hopefully next time it won't be 8 years or 7 years or whatever.
yeah, that's,
Come back and talk about gems at some point or whatever.
Yeah, that would fascinate me in particular. I want to hear about that. I was thinking of an amazing piece of it. Right, thank you very much. And I'll shut down the broadcast.